The last part of the polynomials topic is this idea of let's create a new polynomial using the roots of another. Now, where is it useful? Well, you got this sort of thing. You know alpha, beta and gamma are the roots of a particular polynomial. But you want to create a new equation which has the roots 1 on alpha, 1 on beta, 1 on gamma. Why would you want to do that? Well, maybe you've got a question which says find 1 on alpha plus 1 on beta plus 1 on gamma. Well, if you can find a new equation with those roots, then all you've got to do is go sum of the roots. And then you could say, if they then say, well, what's 1 on alpha squared plus 1 on beta squared plus 1 on gamma squared, you can go to the new equation and say, well, that's just the sum of the roots squared, which I know is the sum of the roots 1 times squared minus 2 times. So it can make some questions maybe easier to find. So how do we do it? If I want to change it, all I simply do is I go, okay, I'll let y equals 1 on x, rearrange it, so x is 1 on y, substitute it into the original polynomial. And it'll come up with a new equation which will have these new roots. So basically, we're letting y equal the new root, the new solution. Because y will be the root of the new equation, and we're saying the root of the new equation will be 1 over the root of the old equation. And so that's how we do it. We say, well, y will equal 1 over the root. X was the solution to the old equation. Y will be the solution to the new equation. So if it was some constant times alpha, some constant times beta, again, we'll say, well, okay, the new root, y, will equal k times the old root. I'll rearrange it, make x the subject, substitute into the old equation. If it's plus some constant, same idea again. Okay, well, I'll make it y equals x plus some constant. Rearrange it, substitute it in. This one's probably more useful because if I can find an equation which has the roots alpha squared, beta squared, gamma squared, then I just got to go sum of the roots when we want to do the alpha squared and so on. So again, we'll let y equal x squared, rearrange that, we'll get x equals y to the half. So let's look at some of those. There's the original equation, x cubed plus x plus 2. We're going to find a new one which has the reciprocal roots. So I'll let y equal 1 on x, so then rearrange it, x is 1 on y. Substitute it in, there's the new equation, but of course, as that stands, that's not a polynomial. So I've got to turn it into a polynomial. Let's get rid of the denominator. So I'll multiply everything by y cubed. Here's the new equation. The roots to this will be the reciprocal of the roots of the old equation. Some people like to change the y's to x because they feel like the equation should have x in it. It doesn't matter because at the end of the day it's just a pronumeral. And so whether x equals it or y equals it or z equals it or whatever, it doesn't matter. So if we said alpha plus 1, beta plus 1, gamma plus 1, right, let y equal x plus 1, rearrange it, x equals y minus 1, substitute it in. That is a polynomial, of course, but we probably wouldn't leave it like that. Let's expand it out, collect like terms, and there's our new polynomial. So the roots of this equation will be 1 more than the roots of the old equation. By the way, that tells me straight away I now know a root of the old equation. What would one of the roots of the old equation be? Can anyone see it straight away? Because there is a root of this equation which will be 0. 0 is 1 more than minus 1. So minus 1 must have been a root of the old equation. Here's the tricky one. Alpha squared, beta squared, gamma squared. So we'll let y equal x squared. X will equal y to the power of a half. Sub that in. Now, of course, there's no way that's a polynomial because we don't have fractional powers. So you think, oh, that's all right, I'll just square it. Problem is, when you square, remember, you get twice the product. So when I go twice 2 times y to the half, I've still got a fractional power. No good. So before you square it, what you have to do is move some terms. Okay, I've factorised it and then moved a term. But notice, everything on one side has a fractional power. Everything on the other side doesn't. So the only term here that didn't have a fractional power was 2. That's why I've now got negative 2 on the right-hand side. I can now square this one because I can pull out the common factor now, because everything has a fractional power. Y to the power of a half, when I square it, it's fine, because that'll go to y to the power of 1, and the other one will be y plus 1 all squared. and we can end up creating a polynomial. Expand out, bring the 4 back over, and there's our new polynomial. So with these fractional powers, before you do the squaring, whether you factorise first like I did here, or whether you move things first, that's I guess up to you. But isolate anything with a fractional power on one side of the equation, anything without a fractional power on the other side of the equation. Then it should be okay to go and square. What about the reciprocal of the roots squared? So y equals 1 on x squared, so now x will equal y to the negative a half. Substitute that in. Again, we've got this problem now not only with fractional powers, but negative powers as well. I'll still factorise like normal. Whenever you factorise, remember you take out the lowest power. Minus 3 on 2 is the lowest power in this one. How do I sort out the negative? Well, it's all right. I'll multiply by y to the 3 on 2. So now on the other side, all of a sudden the fractional power is now on the other side. But it's a positive power. Because remember, y to the negative 3 on 2 is simply 1 over y to the positive 3 on 2. Get rid of the fraction, put it to the other side by multiplying. It's now a positive power. Y to the positive 3 on 2. So I've sorted out the negative indice, square both sides, and we sort out the fractional indice. Now we can expand and tie it up and get a new equation. So if we now have a question, find alpha squared plus beta squared plus gamma squared. Yes, we could go back to the original equation and go, let's find the sum of the roots 1 at a time squared minus 2 times the sum of the roots 2 at a time. We come up with negative 2. But now we can go back to our new equation, which was part C in our example, where we found a new equation with roots. And we're simply going to say, well, that's going to be minus b on a of our new equation. It's just the sum of the roots of this new equation, which again turns out to be negative 2. So that, I guess, is one reason why we want to have this sort of technique, creating these new equations. Okay, so just a handful. They're big hands, mind you, but just a handful to do.